Designing and building spacecraft for interplanetary travel and exploration requires careful planning, engineering expertise, and consideration of various factors. Here's an overview of the process. Mission planning. Define the goals and objectives of the interplanetary mission, including the destination, scientific objectives, duration, and payload requirements. Consider factors such as orbital trajectories, planetary environments, and communication windows. Conceptual design. Develop conceptual designs for the spacecraft, taking into account mission requirements, technical constraints, and available technology. Determine the spacecraft architecture, propulsion system, power source, communication systems, and payload accommodations. Systems engineering. Conduct systems engineering analyses to ensure that all spacecraft subsystems work together harmoniously. Define requirements for each subsystem, including propulsion, guidance and navigation, thermal control, power generation, communication, and life support. Propulsion system. Select an appropriate propulsion system for interplanetary travel, considering factors such as fuel efficiency, thrust-to-weight ratio, and mission duration. Common propulsion options include chemical rockets, ion propulsion, solar sails, and nuclear propulsion. Structural design. Design the spacecraft structure to withstand the rigors of launch and space travel, including structural loads, vibrations, and thermal stresses. Use lightweight yet strong materials such as composites, aluminum alloys, and titanium. Thermal control. Develop thermal control systems to regulate temperatures inside the spacecraft and protect sensitive components from extreme heat and cold. Use passive and active thermal control techniques such as insulation, radiators, and heaters. Power generation. Choose a power source for the spacecraft, such as solar panels, nuclear reactors, or radioisotope thermoelectric generators, RTGs. Ensure sufficient power generation capacity to meet the needs of onboard systems, instruments, and communication. Guidance and navigation. Implement guidance and navigation systems to accurately navigate the spacecraft through space and reach its destination. Use sensors, star trackers, gyroscopes, and onboard computers to calculate trajectories and make course corrections. Payload integration. Integrate scientific instruments, experiments, and other payloads onto the spacecraft, ensuring compatibility with the mission objectives and spacecraft constraints. Consider factors such as mass, volume, power consumption, and data transmission requirements. Testing and validation. Conduct comprehensive testing and validation of the spacecraft and its subsystems to ensure reliability, functionality, and safety. Perform environmental testing, including thermal vacuum testing, vibration testing, and electromagnetic compatibility testing. Launch and deployment. Prepare the spacecraft for launch and integration with the launch vehicle. Coordinate launch logistics, including launch vehicle selection, mission trajectory planning, and launch pad operations. Monitor the spacecraft during launch and deployment to ensure a successful mission start. Mission operations. Monitor and control the spacecraft throughout its interplanetary journey, including trajectory adjustments, instrument operations, and data collection. Establish communication links with ground control stations and mission control centers to receive telemetry and send commands to the spacecraft. By following these steps and leveraging the expertise of multidisciplinary teams of engineers, scientists, and mission planners, spacecraft can be designed and built for successful interplanetary travel and exploration, advancing our understanding of the solar system and beyond.